Here I have several different equations, and we're going to look at these and identify if they are redox reactions. Redox is a concatenation of reduction, oxidation, because reduction and oxidation, they always go together in pairs. Whenever you have oxidation, you also will have reduction. Okay, so we're going to look at these reactions and first of all identify whether they are oxidation reduction reactions, and if they are, we're going to identify the element that is oxidized, the element that is reduced, as well as the oxidizing agent and the reducing agent. Okay, so let's take a look at this first one. We have iron metal, okay, all by itself, no charge, so that's the metal, plus magnesium sulfate to produce iron 2 sulfate plus magnesium, okay, the magnesium metal. So the first thing we do, we say, is this a redox reaction? And the answer is clearly yes. We know that because we see this iron in its elemental form and then in a compound. The magnesium in an elemental form and in a compound. So we know that this has to be a redox reaction, because when iron is, or any element is in its elemental form, in other words it's uncombined with any other element, it always has an oxidation state of 0. Okay? And so both the iron and the magnesium have a 0. But when they are combined in a compound, it is not 0. Okay? And in this case, we look at that, and this is, for the metals, it's just going to be the charge of the metal. Okay, so magnesium it always has a +2 charge. So the oxidation state here for the magnesium is a +2. Okay, so you can write it as a charge if the charge is applicable, or I'm just writing the oxidation numbers below here. I could put that down there to be consistent for those. Okay, and here the iron. Okay, sulfate is a -2, so the iron is a +2 here. All right. So now we don't even have to look at the oxidation numbers for the sulfur and the oxygen, and the reason is we see SO4 here, and we see that same SO4 on the product side. Okay, the same thing on both sides of the equation indicates that there's no change, right? Oxygen, well, oxygen is always -2 when it's in a compound, unless we're talking about special, unusual compounds like peroxides or something like that. But in this case, we have SO4. We have 4 of those -2 charges, so that's -8, which means the sulfur must be not +8, but +6. Why +6? Because the sulfate has a -2 charge. So we have to, these need to add up to that -2 charge. -2 times 4 is -8, plus 6 is -2, the charge of the sulfate. Okay, so that's how we know that. And then we do the same thing over here, and it's a +6. So we don't really have to do, if we recognize that it's the same ion and nothing has changed, we don't have to even go through that process, because we know it's going to be exactly the same, because that sulfur is in the same environment. It's with SO4, and they both have a -2 charge. All right. So really the redox part of this reaction is happening with the iron, where iron is going from 0 to 2, and then with the magnesium, where it's going from 2 down to 0. Okay, so which one is being oxidized? Which one is being reduced? Well, there's a few different ways actually that we can look at this. We'll consider two of them. One of them is to look at it in terms of the electrons. Okay, iron is neutral here, whereas here it has a +2 charge. That means it lost 2 electrons. Okay, and you remember the acronym Leo says GER. Okay, silly little acronym, but it works to remember a loss of electrons is oxidation, and a gain in electrons is reduction. So if we're losing electrons, that tells us the iron is oxidized. Okay, and therefore we know that the magnesium must be reduced. But let's look at this, and sure enough, +2, if I gained 2 electrons, it would become neutral because those electrons are negative, so that would become neutral. Okay, so the magnesium is reduced, the iron is oxidized, and I should be, well, yeah. All right. Now, so we can look at it in terms of electrons, losing or gaining electrons, oxidation or reduction. We can also look at it directly in terms of the oxidation number. It's called the oxidation number because it tells us how oxidized it is. All right, 0. So the larger the number, the more oxidized it is. So 0 to 2, it's becoming more oxidized. 2 to 0, it's reducing. The oxidation number is reducing, and that's where we get that that term. So either way, we come up with the same thing. We find that the iron is oxidized, the magnesium is reduced. Okay. Now let's look at this in terms of the oxidizing agent and the reducing agent. Okay. The oxidizing agent is the substance that oxidizes, in this case, the iron. Okay, so what is it that that causes the iron to go from 0 to +2? Well, it's this magnesium sulfate. Okay, so the whole compound is my oxidizing agent. Okay, I'll just note that here. This is my oxidizing agent because it's the one responsible for the oxidation of the iron. Right? Now, what's the reducing agent? Because remember, these come in pairs, so wherever there's an oxidizing agent, there's a reducing agent. In this case, we're looking at what is responsible for reducing the magnesium from 2 to 0. Well, it's the iron. It's when we combined it with the iron that it reduced this down to the magnesium metal. Okay, so it's the iron that is our reducing agent. All right. So kind of running out of space there, but you get the idea. So talking about the whole substance, all right, the iron, which in this case is just the element, but here we're talking about the magnesium sulfate. Now, it didn't have to be sulfate, because the sulfate we saw didn't participate in the reaction, actually, or in the reduction or oxidation of the iron or magnesium. But it's we had sulfate in our equation, and so it's that compound of the magnesium with that sulfate that is my oxidizing agent, and the iron by itself was what we used to reduce the magnesium to its metal. Okay. By the way, this is the terminology is what they use in mining. Like you say you reduce the ore to the metal. It's being reduced to that metal, because whenever a metal in an ore, whether it's with sulfate or oxygen usually, you have that ore, it has a positive or some kind of a positive charge with the metal, whatever metal it might be in an ore, it's always going to be combined with some kind of a positive charge. And then, so it's always a reduction to get it to the neutral metal. And so the process, for example, like taking aluminum oxide, which is the aluminum containing ore that's found in the earth, the process of reducing that to the aluminum metal, right? That's the terminology that we use. That reduction is also used in the mining industry, where you reduce the ore to its metal. All right. So anyway, let's move on. Not get too distracted here. Here we have another reaction. And we look at this, and remember, just like we looked here, we knew we didn't have to look at the sulfate because it was the same on both sides. I did just verify that, +6, -2, but we didn't have to do that, okay? And this one is somewhat similar, but let's just go through this. We know that the sodium is always going to be the same in a compound, okay? Unless it's going to the metal, which it isn't here. Sodium is +1, sodium +1, so I don't need to write that. It's not changing, okay? The oxygen, the hydrogen, they are always +1, -2, +1, -2, wherever they're found in the equation. And whatever chemical, as long as they're not in their elemental form, if they're combined in something, +1, -2. All right. So I really don't need to worry about the water or the sodium hydroxide, and for that matter, I don't even need to worry about the sodium chloride. Okay, because the Cl is Cl minus. Just looking at its charge, when you have a monatomic ion, the charge is its oxidation number. So ammonium chloride, sodium chloride, I don't need to worry about the chloride, the sodium, the hydrogen, the oxygen, none of those. So my only question is what's happening with the nitrogen, okay? And maybe it isn't completely evident right at the beginning, but let's look at this. First of all, here in ammonia, I know my hydrogen is +1. I have 3 of those, and it's a neutral molecule, right? So my nitrogen must be a -3, right? And I look over here, and this time I have 4 hydrogen, all right? Hydrogen is always +1, and therefore the nitrogen must be, remember, ammonium has not a 0 charge, but a +1. So 4 of those on that -3 gives me a +1, right? So again, no change, all right? Nitrogen, -3 on both sides. And actually, we saw that it would have to be that way because that was the only element in question, right? I saw that the sodium, the chloride, the oxygen, the hydrogen, they're all fixed. They're all the same charge. They don't change. None of them are going into their elemental form. And that would only leave me with nitrogen. And well, I'm not sure about nitrogen. It looks like it might be different here because it's in a different compound. But it's only one, so it can only be oxidized or reduced. And they always will come in pairs. If I have reduction, it necessitates an oxidation. It has to give those electrons to something. It can't just, you can't just have a reduction without a corresponding oxidation. So no matter how you look at it, this is actually not a redox reaction. There's no change in any of the oxidation numbers on the left to the right. Okay? Now let's look at another example. Okay. C2H3O2, and this big long equation, potassium carbonate, water, carbon dioxide, and potassium acetate. Okay, so, and here's my acetic acid. Now, again, we don't have to go through and, okay, what's carbon, what's hydrogen, what's oxygen? I don't need to do that because I see this is C2H3O2. I know that whatever oxidation numbers they are over here, I'm going to have those same oxidation numbers over there. So there's not going to be any change from the acetate here to the acetate there. Okay? And just like before, whenever oxygen is combined in a compound, it is -2, except for special circumstances. So, you know, it's always going to be -2, and the hydrogen, always +1. And so you can see already this must not be a redox reaction either. Okay, my potassium ions are always fixed at +1 because it's a metal ion. The only one in question here would be the carbonate. Okay, because here it's going from CO3, here it's CO2. Okay, but this is CO3 with a -2 charge, right? The carbonate ion, this is my, I was writing the oxidation number for the oxygen, but the CO3 has a -2 charge. So that means my carbon would be a +4, right? -6 from the 3 oxygens, each one a -2, times 3 is -6, plus 4 equals -2, right? Whereas here, even though I only have 2 oxygen, that's 2 times the -2, that's -4. It's +4 still because this one is neutral. All right. So again, not a redox reaction. Okay. Now let's continue here and look at this one. And this one, right off the bat, we know immediately it is a redox reaction. Why? Because we have an element and then a compound with that element. Okay, the element, or its elemental form, and then in a compound. So we know here our oxidation number is 0 for the elemental substances. And in the compound, okay, hydrogen is a +1. What's aluminum? Just the charge, because it's that metal ion, so it's going to be a +3. Right? We need not go any further. We don't have to worry about the sulfate for the same reason that we've discussed before. It is the same on both sides. Right? So we know that whatever the oxidation numbers are, they're not changing, so that's not part of our oxidation reduction. Okay? So what's being oxidized, what's being reduced? And by the way, you'll notice I have these equations balanced, but we're not really paying attention to the coefficients. So this is one exercise where you don't really even have to have the equation balanced in order to determine what's oxidized, what's reduced, what's the oxidizing agent, and what is the reducing agent. Okay? So what is the element that is oxidized? Remember, it's an element that is oxidized. We went from 0 to +3. That's an increase in the oxidation number, meaning that is what is oxidized. The aluminum is the element that's oxidized, which means the hydrogen must be reduced. And sure enough, +1 to 0, that's a reduction. The hydrogen is reduced. So what's the oxidizing agent? Okay, if the aluminum is oxidized, then the agent is what we combined with the aluminum to oxidize it. That would be my sulfuric acid. Okay, this is my oxidizing agent, and the hydrogen is reduced. So it's the reducing agent is what I combined with the hydrogen or the hydrogen-containing compound in order to reduce it. Right? So the aluminum is my reducing agent. Okay? So you kind of just, they're interrelated. Here's the one that's being reduced. So you look at the one that's oxidized, and it is in the compound that is the reducing agent. Okay, let's look at this one here. And I kind of balanced this after the fact. I wrote a little bit close to the paper. But anyway, let's look at this closely, and we can say, because this is elemental, all right, we know this must be a redox reaction. Okay, so what is happening here? The oxygen is going from 0, and what is it over here? It's in a compound, so it's -2. Right? And the zinc is +2, +2. So the zinc isn't changing. We don't have to worry about that one. The sulfur, that's the only one left, right? So it has to be changing. It's a -2 over here, because zinc is always +2. And what is it over here? Well, the oxygen is -2, but I have 2 of those, so that's -4. So here it's a +4. All right. So which one is oxidized? Which one is reduced? Okay. The sulfur is going from -2 to +4. Okay. So that is definitely an increase in the oxidation number. It is being oxidized. Okay. And a little hint, when it's oxygen and you're reacting something with oxygen, you are oxidizing it. Okay, so the sulfur is reacting with the oxygen, and so it is becoming oxidized. Also part of the origin of that term, oxidation. It's reacting it with the oxygen, and so it is oxidized. Okay, and the oxygen itself is reduced. Okay, 0 to -2 is a reduction. All right. Let's determine the oxidizing and the reducing agent. Well, the oxygen itself must be the oxidizing agent, right? It's what is oxidizing the sulfur, and so this is indeed our oxidizing agent. Okay. Except in maybe one example with oxygen and fluorine. Oxygen, if you have it in this scenario where it's reacting with another element, it's going to be your oxidizing agent. Okay. And the sulfur, or rather the zinc sulfide, so the oxidizing agent, remember, it's the whole molecule, okay, is the oxidizing agent. So it's the zinc sulfide that is my reducing agent. Okay, that is what is reducing the oxygen from 0 to -2 is my zinc sulfide. Okay.